One more.
All right. Well, I'm going to get started. I have the recorder on, and let's go ahead and get started. I just realized that you guys do not have an active homework as of now. So I'm going to give you guys a new homework assignment. We're going to talk about it also. Okay, so that's really the best kind of thing because I can give you the homework, and then you guys can, we will talk about the components that you need to get it done, and then you can go ahead and do it. All right? So the homework assignment has to do this. You have to write a program to do this. I will give you you cannot use any type of dot data section. Okay, and then your program needs to reverse all the characters coming in from a file and then send the reverse string to the output. So standard in, you read it in, and then with standard out, you have to print the reversed version of whatever is coming in. But you cannot, you cannot do anything with dot data. There's no variable you can use in this particular program. But you can use the stack. Okay? So are there any questions about this program at this point? How many people think that we have not talked about enough concepts to get this done? Maybe. Okay. Okay, so it depends on whether you look at it this way. Yep, go ahead.
How big a file?
How big of a file?
It's less than 64.
How about I just say that, I will not give you a file so big that it will overflow your stack. Oops, did I just say something? Like to give away a part of the solution?
Yes.
Yep, it has to do with the stack. The recorder is on, yes.
Are you sure about that?
I'm sure about that, yes.
All parts of it?
Let's double check. Let me replay the file as it's still recording. You can actually do that, by the way. You guys know that, right? You can replay a partially recorded file like right away. I have done it in the past because somebody asked me, what did you say about 2 minutes ago? And I have no idea what I just said 2 minutes ago. So I was to replay the video of about 2 minutes ago. That's what I said. All right, so that's what we'll do today. But before we do anything like that, we'll go over the concepts of pushing and popping first, okay? Because those are very important concepts, and it's going to be very useful in this case, okay? All right. So let me go to the website of this class. And we are now in topic 6. Okay, so let's focus. Okay, so we are now in topic 6, actually topic 7 now, because we are talking about a stack. So what you really want to do is to go to topic 7, and definitely I would read this part here. I scanned the entire participation report of the entire class. So out of about close to 60 people, I would say about 12 to 15 has visited or clicked on the link. Yes?
What about the most of the notes in the book? I usually read off that one rather than off.
If you have the whole book, the link to the whole document, then it doesn't count that because you have to go from the link directly. But I don't know how many people actually do that too. Yep. A few. Okay. But I have a suspicion that out of the remaining 45 people, maybe half of those people have not actually clicked on anything. I just read this topic. The PDF works too? Okay. Yep. Okay. All right. So reading is important because if you read ahead of time, at least you will have some idea of what I'm going to talk about. And then after I present, the sample programs and talk about the concepts, then you can read it again if you need to. If you feel like, okay, I better read it again because there's something that I might have missed. So it is important to read the notes and also to take notes in the class too. Even though everything is recorded, it is still useful not to record, not to write down what I have, what I'm recording, but to write down, the important concepts that I'm talking about. Okay, because even though when I'm talking about something may cross your mind and say,
oh, okay, I just suddenly realized what he meant by blah, blah, blah. Write that down. Because otherwise, that would just kind of pass you by. My recorder cannot record your thoughts, fortunately.
Yeah.
So you have to write down your own thoughts as you are going through the class and looking at the sample programs. All right. So we'll go over this part kind of relatively quickly. This is the stack pointer that is called ESP, and the stack rolls down to lower addresses. In other words, when we have more stuff on the stack, the value of ESP is getting lower and lower. The push and pop instruction, to push a value is to put a value onto the stack. To pop a value is to retrieve and remove a value from the stack. So one is to put something into it, and the other one is to remove something from the stack. Push is like this, okay? There are only certain variants of push. You cannot do a push B, by the way, okay? You can do a push W to push 16-bit on the stack. You can do a push L to push 32-bit on the stack. But you cannot do a push B. There's no way to push a byte on the stack. That instruction does not exist. Push F is to push the flags, all the system flags, including the carry flag, the overflow flag, and stuff like that onto the stack. Push A pushes all the registers, and then pop A pops all the registers. So the next slide talks about all the reverse operation. So all of these instructions will put something on the stack, and then all of these instructions will remove something from the stack. Okay. So pop itself expects one single operand, and when you push and pop, the assembler does not enforce whatever you're pushing or the width of what you're pushing is matching whatever you're popping. So you can do things out of order, out of size, and have things messed up because of that. If you do a push W and then a push L and then do a pop W and then a pop L, things will look kind of weird. Okay, we'll talk about that and actually play with it later on today. We have push F, pop F to correspond to push F. In other words, it will restore all your flags. So after a compare, you can use push L to you can use push F to remember the carry flag, the overflow flag, the zero flag, and so on. And then you can do a pop F later on to utilize those flags later on. Pop A corresponds to push A. In other words, if you just push A to push all the registers on the stack, pop A will correctly pop and restore all those registers in the proper order. So that comes in pretty handy as well. Are there any questions about push and pop in general? Okay, so you have usually they come in pairs. You have push L, then you have pop L. You have push W, you have pop W. You have push F, and then there's pop F. Push A, pop A. Is that okay? But for the most part, we only use push and pop on a register basis. That's the most common type of push and pop operation. So here's an example. We push something on the stack, we move something into EAX just to reset its value, and then we pop it back in just to validate that the pop instruction works. Okay. All right. So time for some sample programs. So we'll go ahead and take a look at a particular sample program. So we'll go to cisp310 and write a sample program to play with a stack. I'll just call it stack1.s. Question? Okay, so let's focus. Okay. So we'll take a look at a sample program to kind of make use of the stack. The most typical use of the stack is to save the content of something so you can use it later on. Okay? Because after all, we only have a few registers. Okay? Even if you count all of the registers, we have about 8 registers. And you can run out of stuff or run out of registers to store the result of something really fast. Now, you can use memory locations, but memory locations has a problem. Okay? Whenever you start to use the dot data, we can run into problems in the future. Because right now, we have not talked about subroutines yet. We have not talked about reentrancy. We have not talked about a lot of other stuff that cannot really use statically allocated memory. Just to give you a preview of what kind of problems we can run into, how many people at least have heard of the concept of recursion? Okay, everybody? And with recursion, what is a typical use of recursion? Well, factorial is the most well-known example of using recursion. But to do recursion, what is special about recursion? It's a subroutine calling itself, right? And if you do recursion, each time you call the subroutine, it has a parameter, right? It has an argument. Would all the different invocations get mixed up about the parameter?
No.
They don't, okay? And the reason why they do not get mixed up is because they're all stored on the stack. If it is statically allocated, they will get messed up, right? Because when you call the same subroutine the second time, the parameter of the first time would have been lost already. So the reason why it's not lost is because it is stored on the stack. So when you invoke the same subroutine, let's say 5 times because of recursion, there are 5 parameters on the stack, concurrently being there in a specific order, last in, first out. So that's something that we will take a look into later on in this semester. But for now, we're going to look into just push and pop. But this is the foundation of all of that stuff that we will have to talk about later. Okay, so we'll start with a fairly simple program that does not even use dot data at all, but we'll be messing around with data. We'll be actually be storing and retrieving stuff with this program. When you use push, you can use just about any operand that you want to use. In other words, because this is a source, okay, you're specifying what do I want to store on the stack. It can be immediate, can be register, can also be any memory operand in the case of the i386 processor. So in this case, I can do a push long, a constant. Okay, so I can say 0x ABCD1234 as a 32-bit number. And just to be sure, I'm going to move a 0 into EAX. I'm just going to reset the value of EAX for sure. And then I'll do a pop L into EAX. Okay, this is my entire program. Not very complicated. Its only purpose is to illustrate how push works and how pop works. But it's going to take me a little bit of time to finish this demonstration because I want to show you also during the process, after each and every instruction, what is happening to the stack pointer and also what is happening to the memory content pointed to by the stack pointer. Because those are the actual important things when we want to understand what the stack is actually going to do. And this relates directly to what we talked about on the other day on Tuesday. Remember on Tuesday, I introduced 2 pseudo C code that talks about pushing and popping. This is directly related to that. All right, so we have this program, and let's go ahead and get it to work. G stabs -o stack 1.o stack 1.s, and then do the linking stack 1 stack 1.o gdb stack 1, and do a list. We'll put a breakpoint on the very first instruction because I need to take a snapshot of the stack pointer and memory content and stuff like that at that point. Okay. Are there any questions before we get started with this program? What do you think will happen when on line 5, after line 5 executes, what do you think should be in EAX? The content that I pushed earlier. Okay. All right. But the question is, how does it work? Okay. How does this stuff actually works? Right. So we'll run the program, which stops right away because I put a breakpoint on the very first instruction. Right at this point, it doesn't seem to make sense to take a look at registers because I have not done a single thing. But it does make sense because I want to take a look at the stack pointer at this point because it will change because of the push L instruction. So I want to take a snapshot of the ESP register and just kind of briefly remember the number. There's no need to remember the entire number. In fact, I can scroll back up again later on. But it is important to kind of notice that it is ending with C0. Okay? All the other digits are not really that relevant because we're pushing a very small amount of stuff on the stack. It's not going to change all that much. But C0 as the least significant 2 digits here is kind of important because we want to use it for comparison purposes later on. Okay, so now we'll single step, and the push instruction is now done. The first thing I want to do is to take a look at ESP again, and you can see that ESP or the stack pointer has changed. Is it incremented or is it decremented? Has it increased or decreased? It has decreased by
32 bit.
what is 10 minus C in hexadecimal? 10 in hexadecimal minus C in hexadecimal. 10 in hexadecimal is representing what in base 16, and C is representing what? 12. So the answer is 4. The difference is 4. Okay. What do you think here, or what do you think on line 3 that has to do with 4? 4 bytes. Okay, exactly. It's a push long instruction. It's pushing 4 bytes on the stack. So now the question is, well, I know that that constant is now saved on the stack, but exactly where is it on the stack that it is saving it? Remember what is the definition of the stack pointer? It points to the lowest byte of the last thing that it pushed on the stack. Hey, that means the stack pointer should be pointing at exactly that value on the stack right now. Let's double check. And how do we do that? I'm just pretending to forget. I'm not actually forgetting. just in case someone thinks, Tech is forgetting how to do this. No, I have taught this class enough times that even if you knock me with a baseball bat, I will still be remembering that. I will still be remembering how to do this after I forget my own name, which is actually less important in many ways. Yes?
I want to test that theory.
After class, we'll take it outside.
Tonight?
You may want to do this after you get a grade out of this class.
Really?
We need to move.
Because I have a dead man switch on the Moodle server. Go ahead.
We just have to find
We
it
need
first.
to move indirectly ESP
Yep.
using others in ESP like as indirect move operators.
Indirect. You can use an indirect operand with the push L instruction. That was not your question.
No, as I understand, you want to see in memory how. So you memory stored in ESP. You can use ESP like indirect operand. to
Yes.
do
Well,
something.
not an indirect operand, but as the address, it can tell GDB where I want to examine. So we'll take a look at this command here. It will basically explain what we need to do. So I'm going to change the preferences because I have to change the font appearance, change the font size back to 15, let's say. Much better. You're welcome. Okay, so we want to use the X command because it examines memory location. And we want to show, well, the first time we'll just show the entire 32-bit thing, which is W, in hexadecimal, which is X. Okay? And then we want to specify exactly where ESP is telling me. $ESP in GDB is referring to the value of ESP, the register. Okay? But remember, you have to use a dollar sign here because it is not a usual variable. It is a special system variable in this case. Guess what? Oh, we got the same stuff here. Okay? So the push operation is doing exactly what we talked about last time. The first thing it does is it would decrement the stack pointer by the size of the thing that we're pushing on the stack. And then the second thing it does is to copy whatever we want to push on the stack to those memory locations. Are we still doing okay so far with those concepts? It is still related to what we talked about on Tuesday. Okay, the C code, the pseudo C code that we talked about on Tuesday is actually showing you exactly the same thing.
How is it writing up all value on
How is it?
writing a value on this, like not store a value in register?
It's not, well, it's just, I'm just showing you the mechanism of pushing it off.
So it doesn't make sense like putting a value on the register, like if we do like a move function, like
It can be done like that, but there's a special thing about this, is I don't have to declare anything in dot data. It has no name, and I can do this, like, well, not infinitely, but close to. Okay, I can push like 64 kilobytes on the stack. I chose 64 kilobytes because that's also the window of the part bleed debug. Well, that's one thing that's always in my mind right now. So
Change of passwords.
yeah. All right. So what we want to do now is to single step through the second instruction. The second instruction is a simple move long 0 into EAX instruction. So we want to single step through that and then take a look at EAX. Not surprisingly, EAX now has a value of 0. Now I want to do something. Let me see. Let's see what is happening to the stack pointer. Okay, the stack pointer should not have been changed since the push instruction. Well, sure enough, it has not been changed. Now this is the next instruction that we have to kind of pay attention to, because we are now ready to execute the pop L instruction. The pop L instruction is the reversal of the push L instruction. What it does is it will copy whatever the stack pointer is pointing to at this point to the register that I've specified in the destination. So in this case, in pop L, the only operand has to be a destination operand, which means it cannot be an immediate operand. It can only be registered for memory. Okay. And then after that, it will also change the stack pointer to quote unquote reclaim the space used by those 4 bytes previous. Okay. So it's not really just a move instruction. It is move followed by quote unquote clean up. Okay. So we'll take a look at what happens after this. The first thing we want to look at is EAX. Okay, EAX now gets the value that we are popping. Previously it was in the memory content area. That's good. But we also want to take a look at ESP, because ESP is now back to its original value. We push something, we use the 4 bytes, and then we pop it by copying those 4 bytes into another location, and then we move the stack pointer back up to basically say those 4 bytes are not needed anymore, and it is now basically reclaimed. It doesn't disappear, it is just reclaimed. Yep.
What do you mean about clean up? Does it really clean memory? What if we now look there? Probably it's still here.
It is still here. You're absolutely right. Okay, so that's a very good question. The question is, what is going to happen, or what is happening right now, to the memory location 0xBFFFBAB?
ESP minus.
Still down.
Well, oh, you mean you want to know what the content of what ESP is pointing at right now, or
ESP
previously?
minus 4.
-4. Okay, so we'll take a look at that location. So we'll do an x slash, once again, just WX, and then we'll just go ahead and copy, this particular value here.
ESP minus 4. ESP minus 4.
But ESP minus 4 may not work because ESP may have a type associated with it, so that may not work. So I want to just be sure and just do that, and you will say, oh, it's still there. Okay, that's only because we don't have any interrupts happening to a user process. Okay, if we do have interrupts or signals happening, then you have no guarantee of the content of anything that is below ESP.
But it is not clean it up. It just left it here. Just moved point.
Correct. You are moving the point. You're moving a bookmark to basically that defines which part of the stack is in use and which part is no longer in use by your program.
Yeah.
Okay. So that it has no guarantee whatsoever that that location can retain that value from here on, because an interrupt happens, it can use up that location. A signal happens, it can use up that location. Now, because we're using a protected operating system, interrupts cannot use that location. It will be using the system stack instead of the user stack. So that's why we don't see those effects. But when you do embedded system programming using a operating system that has no protected mode, then you will start to see all that stuff changing for no apparent reason, because it's the interrupt that is changing it. Yep.
What is the capacity of ESP?
What is you mean the full size? How far it can go? Well, that's a good question too. Let's test it. We'll test it by using another program, and we'll run it on the side because it takes a while to get to that point. Okay. I actually have a pretty good idea of how far it can go, but we'll just write the program just for the sake of doing it. Okay. Okay. So I'll name this program "How big is the stack?" .s. And we switch to the .text section, which is by default already there, so we don't really need it. Underscore start, and the only thing we're going to do is to say push L $0, and then we say jump to start. This is the tightest loop I can make that will keep pushing stuff on the stack until it runs out of space. Is that okay? Now, obviously I can say push out, push out, push out, push out, push out, and then jump. But why do that when I can have like a 2-line program, 3-line program that can do exactly the same thing, right? Okay, so I'll just compile and run this program in GDB until it crashes. Because at some point, we'll run out of space. Basically, we'll reach the point where the system will say, well, you can only write down to this location. Anywhere lower than that is not allocated to this process. And then at that point, we'll get a segmentation fault because I'll be attempting to access a location that this process is not supposed to. But if you do this outside of GDB, you will just get a segmentation fault. But if you do it inside GDB, you can at least go back in and examine the value of ESP at that point, so we know exactly how far we can go before we run out of space. Okay, so let's go ahead and do this one. G-steps-O, how big is the stack.O, how big is the stack.S, LD-O, how big is the stack, and then how big is the stack.O. GDB, how big is the stack? I really like, auto-completion. When you have files named like that, it's really helpful. Okay, and then we'll just go ahead and run it. Okay, that is fast. That is really, really fast.
Maybe small.
And that's it. That's the ESP. Okay, let's do the whole thing all over again. Because
probably we need to read.
yeah, we have to find out what it was before. Yep, you're right. Okay, so we'll go ahead and put a breakpoint. Okay, let's list the program, put a breakpoint on line 4, run the program, do our IRESP first, and then we'll delete the breakpoint. Okay, when you want to delete a breakpoint, you have to delete the breakpoint by its ID or its number. The breakpoint that we just set is breakpoint 1 because it is the first breakpoint. So when you say delete a breakpoint, you use the same number and delete breakpoint 1. And now we can continue the execution of this program, and it's done. Okay, so we are now out of space. It didn't take all that long. It used to take a lot longer. Maybe it's the PC. Maybe I was running a PC that's really, really slow before. Okay, well that's okay. We'll just go ahead and find out what the differences are. So we can say print, and we want to pick up this number, and then say minus whatever ESP is at this point. Arithmetic to argument to arithmetic operation, not a number or boolean. Okay, let's see. Can we show ESP at this point? Yes, we can. So now we can do the same thing again. Just say minus this number, and we have the end result here. This is how big the stack is for a user process. It's what, 8 gigabytes, 8 megabytes, 8 million bytes or so. Right? I mean, we got 6
8 million.
digits, after the 8. Yep. So it's about 8 megabytes or so. So that answers your question. We have about 8 million bytes or so on the stack.
This is in hexadecimal. Hexadecimal.
This is in decimal, not in hexadecimal. Yeah, print by itself prints in decimal, so until you say print /x, then it will change it to base 16. All right. Is that good enough so far? Okay. All right. So then we'll go ahead and write another program. Okay, remember, your homework assignment, which I will, finish the writing part later on today, is to read the input from standard in and reverse all the bytes and then print it back out again in the reverse order. Okay, and you are not allowed to use dot data at all. Okay, so you cannot declare your buffer and say dot, buffer colon dot buff, or dot byte or dot fill or whatever, and make it really big. Okay. And you can only use the stack. So the question now is, how is the stack going to be useful for this purpose? And how do we connect the concept of reading and writing using system surfaces 3 and 4 and connect that to the stack and the stack pointer? Any questions about that part?
When is it due?
Sorry?
When is it going to be due?
When is it going to be due? How about the Tuesday after the spring break?
How about 9:50 do it? 9:50.
Next.
We'll do it, you know, at the beginning of the class. I do not bargain. No.
Make it due Tuesday at 6:58. Make it due Tuesday when we come back at 6:58.
Well, it is plenty of time to do it because, you know, depending on what I'm giving you as pieces that you can build upon today, it can be done fairly quickly. Okay, this has to do with whether you can make the connection between the concepts or not. We have the concept of system surface 3 and 4 for reading and writing. We have the concept of stack operation, pushing to store something on the stack and popping for, you know, removing something from the stack. So the question now is, how do you get these two concepts related to each other and get it done? Yep.
No, I was thinking you just push them all in and then just read them out. Like you push, or read it, push, read it, push, and then read out, pull, read out, pull, read out, pull.
Because it is already in a last in, first out order. Okay? So what I'll do is I'll give you the non-iterative version of this program. It will only do 4 bytes. But you can extend that program to use a loop so you can use it to deal with any arbitrary number of bytes as long as the stack has enough room to deal with it. Okay? I think that's a pretty fair, you know, starting point. Yep. How many points? I haven't decided yet, but more than the one before. So that's the trend. Okay, each one is going to have more points than the one before. Okay. The point value is not even that important. Well, I mean, it is important, but it's not that important. The most important part is to use the homework assignment to kind of give you a better understanding of the concepts, because you have to play with it. You have to actually figure out how it works. Okay, so this is, you know, this is my little gift to you guys. Okay, you know, this is your starting point.
Thank you.
So we'll call it flip 4 because it will only flip 4 bytes. Okay, and the program goes like this. Now, the thing about, you know, giving you a program as a starting point like this is I'm not going to explain this program itself. Okay, I will test it during class and I will show that it works, but I'm not going to explain exactly how it works because it has only components that we have already explained. Okay, so you will have to kind of connect the dots and say, okay, so that's how this program works. Now, how do I extend this program so that it can deal with, you know, basically an arbitrary number of bytes as long as it is not too large for the stack to deal with. Okay? All right. So how do we read a byte from the input file?
$3 EAX.
Okay. So let's go ahead and do this part first. So move 3 into EAX to specify system surface number 3, which is the read operation, read from the file descriptor, and $0 into EBX to read from standard in. And then we have this one goes into ECX, which is the location that I'm reading into. But since you're not allowed to use dot data or to use any statically allocated buffer, we have a question mark here, at least for the time being. So we'll deal with that question mark in just a little bit. And then we have the last one, which is the number of bytes that we are reading. Since I'm reversing bytes, you know, individually, so we're only reading 1 byte at a time, and then, you know, do something with it one at a time. Okay. And don't forget the last one, the actual software interrupt instruction is also useful because, you know, without that one, nothing's going to happen. In other words, you can look at the first 4 instructions, the 4 move out instructions, as filling in a form to request something. And then the last instruction, the in instruction, the software interrupt instructions, is the ones that actually submit the form to an official or someone who can actually get the work done. So you can fill in the form. If you forget to turn that form in, it's not going to do any good, right? So that's why don't forget the int instruction, because I think some people, you know, occasionally forget about that one. All right, then your program will look kind of funny because it seems like to have everything set up, but it's not doing anything. All right, so when this comes back, you know, I should probably check EAX to see if it is 0, because if it is 0, that means I'm done. Okay, but in this case, since I'm only using this as a demonstration program, I'm not checking EAX. But you should when you write your program, because you have to detect and a file, and then you have to unwind stuff on the stack after that point. But I'm not going to do that. I'll leave that part up to you guys. Okay. Now, what do I do with that 1 byte that I have stored? Absolutely nothing. Okay, because it is already stored at the right place. So the question mark is important, because how am I going to allocate that space to store something, and how do I know that it is okay at this point? Since I said it will read 4 bytes, and without using a loop, this is what I'm going to do. So there are 6 lines that I'm copying. Paste, paste, paste. I'm now reading 4 bytes. The question now is, well, but I cannot be storing all those 4 bytes at exactly the same location, because otherwise they'll just be overwriting each other. So I need some way to allocate the space to store a byte, and I need to do that before each read operation. Are we doing okay so far?
Yes.
With the necessity to get the space to store that byte, and then specify somehow and say, and tell the system surface number 3 and say, hey, that's the place that I want to store that 1 byte. Okay, so with all the instructions that we have talked about so far, especially the one that we have just recently talked about today and on Tuesday, which one do you think can reserve some space?
Stick.
Well, which one? We got push and pop. So pick
Push.
Push. Push. All right. Okay. So where do you think? When do we push something on the stack to reserve some space? Before or after system surface number 3?
Before.
Before, exactly, because you don't want to allocate after the fact, right? You want to allocate the space, and then you tell system surface number 3 and say, hey, store that byte over there, the place that I have just allocated before this sequence of instructions. All right, so we'll have to do some push here. Push L. You can push W. Okay, let's use push W so we can have much bigger files to flip. Okay, so we can use a push W here. So that means, for before each one, I have to do a push W as well, just to reserve the space. Otherwise, they'll be stashing stuff into the same place. What should I push on the stack?
Anything.
It does not matter. Exactly, it does not matter. You can push whatever you want, because my objective is really just to allocate the space. That's all I want to do. I just want 2 bytes, or I really just want 1 byte. But since there's no push B, this is the best I can do without using ESP explicitly, stuff like that. All right, so we'll do this. So we'll do a push W, just 0. Okay, we'll push 0 on the stack, and 4 of those all together. All right, and here comes the real question. Here is, what am I going to tell the system and say, hey, you know what, I want you to read a byte and store that to the 2 bytes that I have just allocated. ESP. Just ESP itself? Percent ESP? Parentheses? Okay, let's think about it. Okay, what is the operand with parentheses around it? It's called indirect, right? So when you specify indirect operand, what is being copied? Okay, let's say you have open paren, percent ESP, close paren. That's the first operand, and then the second operand is ECX. What are you actually copying in that case?
Zero.
It's indirect. It is a memory operand. So if it is a memory operand, where in memory am I copying? Where ESP is pointing to, right? Is that really what I want to copy to ECX? Because what is the purpose of ECX in system surface number 3? It should store the address of where to store that 1 byte that I'm going to read, right? Not the content that is already occupying that location. Am I making any sense here? Now that importance is actually, this is actually very important, because it is differentiating a register operand from a indirect operand. Okay, and that's a very conceptual kind of thing. It's not just details. So in this case, we do not want the parentheses because I am not going to copy memory content to ECX. I'm copying the address of where to store something into ECX. Are we doing okay so far with that concept? Let's go ahead and just specify ESP here. And this one will be ESP2. And this one will be ESP2. And the last one is going to be ESP. And in case nobody has realized, I just lied and lied and lied and lied because I was explaining exactly how this program works while I said I would not do that. Darn it. Bad habit of myself. Okay, so now that I have 4 bytes already read and put on the stack, it's time to put them back out onto standard out. Go ahead.
Isn't that gonna overwrite each time?
No, it's not gonna.
Pushing with the stick.
It's all
Just sticking.
Yep.
Yep.
I didn't see that. Thank you.
Yep. Yep. That's the beauty of the push instruction is you don't have to declare anything. You don't need to use .data and then say, I want to reserve a big chunk of memory because you're just allocating as you go, as you need it. Okay. So now let's go to the opposite side of stuff. Okay. In other words, I'm going to specify a write operation here. So write operation starts with starts with a 4 in EAX, and we specify 1 in EBX because we want to use standard out in this case. We want to specify something into ECX because we want to point it to an address of where am I going to get that byte from to print out. And then we want to specify something into EDX, which is the number of things that I'm printing. So we want to specify $1 into EDX. And then we ask the operating system, let's do it. All right. So what exactly is missing here? Obviously, there's that, but there's also the question mark, right? So what do you think the question mark should be? Now let's think about it. Let's think about the input stream and then the output stream. If the input is exactly A, B, C, D in the file, what is the first character to print? That's the output. As the name of the program implies, put 4. T, right? Okay. What is ESP22?
T.
Okay, well, we can just use it then, right? So that means I can just say, hey, ESP is has the right stuff in it already. Just copy that over. Is that okay? Then we say pop W, and I don't care where I'm popping it into. And then we have, let's see, there are seven lines. Paste, 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 and we're done. Okay, that's our exit instruction. The program is done. Okay, this will, assuming a file does have 4 bytes at least, this will read 4 bytes, flip, and then print those 4 bytes back out in the reverse order. But nobody's gonna buy it. I taught you guys that, right? Never trust me when I'm doing programs like that. Okay, so we'll go ahead. And by the way, this is the first time I write a program like this, so I would not even trust myself. Yep.
Probably you need to move after it interrupt.
Say again?
Move after interrupt.
Move after interrupt. Move what to?
Pop.
Of pop?
Why do you have to pop after the interrupt command? Instead of before it, is what he's trying to ask.
Well, because if you don't pop, then you'll be printing the same character over and over again.
I mean, you need to pop not before reading, but after.
You don't want to pop before. We got it all set up right. Because the transition between the last read and the last write the first write operation has got it right. So we know the order is okay. Because the whole thing about push and pop is they have to be in the reverse order.
Yes.
So that's why the last thing that you push and then you read into it and then you write from it right away and then you pop to get to the next available item.
Because it's block like before reading, so I saw that you put them before.
Well, let's see whether this works or not. Okay, because as I said, I don't even trust myself for with programs like this. So we'll do a G stabs -O flip4.O flip4.S LD flip4.O. Oops. Now, because every time I assemble the program and link the program, I actually just out of habit, I actually say it out loud every single time. I'm assuming that everyone should know these commands by now, like what options or what switches to specify and whatnot. All right, so let's do a GDB flip4, and well, I didn't specify a file, so let me just go ahead and specify a file first. Now, instead of getting out of GDB and then do the VM and then come back in again, you can actually use the exclamation point to shell out. In other words, after the exclamation point, you can run just about any commands just normally as on the command prompt. So this way, I can go ahead and Vim or use Vim to edit my input file, the test input file. So I'll just say test in, and I want this file to be somewhat symmetric. So I will start with an empty line, and then we'll have AB and then another empty line here. Okay, that's my input file. Now I run the program with redirect from standard in from in.test, test.in, and then the output is going to be test.out. We'll capture it using the redirect symbol also. So we ran the program, it is all done, the program exited normally, so it's all good. So let's quit the program and then take a look at test.out. What should be in test.out right now? Line feed, VA, line feed. Okay, because it has line feed at the beginning and the end. So let's take a look and see whether that really is the case or not. And it is. No, Tech, you got it wrong. There's a missing line feed. No, it's not missing. It's there. It just looks like it's missing. The sure way to tell whether it is missing or not is hex dump. Do a hex dump -C, to display character by character, and use test.out like that, and you can see that it is a line feed, a 6.2 in hexadecimal, 6.1 in hexadecimal, and another line feed at the end. So this program does work. So what you want to do is you take this program and then turn it into the form that I want, which is it will read an entire file, and then it will flip and print the content of the file in a reverse form. Okay. Are there any questions about this? Can I show you what? Yep. Okay. Well, you can examine the program later because but unless you want to have anything to ask. Yep.
I was trying to figure out how many. I know you had more push, and you also have more pop.
Yep.
Okay.
Yep. They all match.
But the last pop, is that when we get it in?
The
back
last
to-
pop
back
is
to
only
location?
there to keep everything balanced, even though it is not 100% necessary. But we do want to keep the stack pointer balanced. In other words, if you look at the stack pointer before the entire program executes, and then you look at the stack pointer at the very end of the entire program, you want it to be the same. Yep. You will need some kind of construct to do it. What if your program is stuck in a infinite loop? Well, you have to get out of the loop at some point.
The segmentation falls come out, right? Like you have segmentation fall in the first one, and you have to give it
There's an indicator that you can use to get out of the loop.
that's fine. That doesn't make sense. Like not like if we don't, so we have the same problem as you had in the first one when you did jump, you did unconditional jump.
Yes.
You did zeros and then you unconditional jump. You're going back to start. So it has right away gives you segmentation fall. That kind of stuff is not fall for us. Same thing.
That depends on how you write your program. Then you have to debug against the rules.
The same thing is not come up for us then, right?
It can potentially pop up if you write your program incorrectly. Okay, so any other questions about this program? Now the biggest, yep, go ahead.
I was just curious, because you're using pop or push to allocate number. If you just incremented the ESP, would that do the same thing, or would that do something different?
It will do exactly the same thing.
So you
Because
just add it.
because push and pop, remember from our discussion on Tuesday, push can be emulated by 3 assembly instructions, and pop can be emulated by 3 assembly instructions as well. So yes, you can definitely not use push and pop and use those 3 instructions instead.
Would you need all 3 or just one? Would you need all 3 or could you just do add W?
To do the allocation, you only need 1 instruction.
Just the one command.
Right. To do the deallocation, also only 1 instruction. Yep. The biggest issue is, how do you know when to stop?
Yeah.
When you're unwinding. Okay? So what we'll do today is, we'll introduce, call and return, and those concepts will be very helpful. Okay? To explain call and return, I really only need 5 seconds. It's call and return in C. What again? Say again. The call instruction and the return instruction in assembly is the same as the concept of calling and returning in C.
Can I scroll up a little bit? This one's wording out.
Sorry?
Or the pop. Scroll up a little bit.
So, say again?
Oh, if you can scroll up a little bit. I just want to see where you started the pops.
Right before, right after the last read operation.
Okay.
Okay.
There's nothing below the last one.
Well, I'm going to make this available to all of you guys, so
Okay.
you will have access to this file, along with the next file. Okay, so we'll talk about calling and returning. Calling and returning is very simple once you know what is pushing and what is popping. Okay. What do you think happens when you call a subroutine in C? So let's just say I'm going to use the projector here. And we'll use mouse pad and change the font size. Select font, 16, there we go. All right, so when you have a C program, okay, you say void, F, void, and here's the subroutine. And then inside main, you have a subroutine call to F. Okay, and we can even spell out return here. So the question is, what is equivalent to a subroutine call in assembly? What do you think? Call F. And how do you return from a subroutine? Well, close. It's red. Because we like 3-letter words in assembly language mnemonics. So RET is, well, but hold on, call is 4. So why is call the entire thing and move is not?
Push L.
Push, exactly.
There's
There's no consistency. I don't like that. Okay, but anyway, in this case, it's call F and then a return. Okay, right. The next question is, how is this going to help us with the homework assignment? In fact, how do you organize the program using subroutines in order to get it done? I can give you the C equivalence of this program, and then you guys will kind of have to think about what to do with that equivalence. Okay, because certain concepts we can do it in, okay, in terms of concept, we can do it like this. Okay, so this is the other missing piece of the puzzle. Okay, we'll just call this, ABC. Okay. Yeah, we can do that. It has a single local variable ch. But tag, you just said we cannot use .data. Yes, I did. But this ch is not a statically allocated variable. This is a stack-based local variable. It's an auto local variable. So it's not really statically allocated. Okay? So you kind of have to connect that concept with whatever we are talking about right now. So in this case, it is equivalent to something like this. Okay, so we say if read operation, reading from standard in, reading into ch, and from standard in. If there is something that I just read, then I will call ABC again, and then when ABC returns, I'm going to write to standard out whatever is in my ch, and I only want to write one character. Sorry, I got that one wrong too. There we go. That's the subroutine that you have to write. We have the calling of a subroutine, and then we have an implicit return at the end of the subroutine. So in C, the return is explicit. In C, it is implicit, and in assembly, you have to make it explicit. So I'm going to put a return here just to make it explicit. When I say C, and it is interchangeable with C++, okay, because I'm only using the subset of C++ that overlaps with C. Okay. Are there any questions about this particular subroutine? It is recursive. But in terms of concept, isn't it about the same as what you need to do? And do we have the mechanisms to do all this stuff here? Where is ch?
ESP.
Well, we don't have ch, but we have the stack pointer. Okay, that push W instruction is going to be helpful. Are there any questions about this particular program? If you look at, okay, go ahead.
Why we need it?
Yeah. Why?
Why we need it?
Why do you need the C program, the C code?
Recursion, calls, we can do it in a loop.
You cannot really do it in a loop because you don't know when to stop. Now going forward, you know when to stop, but going backwards, you don't know when to stop. There's no way to easily tell that I'm done at this point. So that's why you have to use subroutines to easily keep track of when you can stop. Yeah.
Will this code copy the file in the right order?
Nope. It will be in the reverse order. Okay. Okay. I can see some doubts here, I'm not quite sure this program is going to work. So let's go ahead and check out this program and make sure that the C version works first, and then you guys will just have to reverse it to or convert it into assembly code.
Can we give at some point an example of how to do a call in assembly? Just call assembly.
Absolutely.
Okay.
We'll do that first. Call and return. Call and return is just like this. You define the label of your subroutine, and then you do a bunch of really useful stuff in it, and then you say return. And to call that, well, let's say we have several levels of calling and returning. Okay, so G calls F, and then it has something important to do. And then underscore start is going to call G, and then it has got something important to do. And then we exit the program. All right? So now the question is, how is this going to work? Okay. This is equivalent to something like this. If I want to convert this program into C, C++, it becomes, this part is basically your main subroutine. So your main is really not doing anything useful, because all your main is going to do is to say G. Okay, call G, and I'm done. Because the exit code of 0 is implicit in C. So if you don't say anything, it is going to return an exit code of 0. This part here is really just saying, okay, here's my subroutine G, which does not really return anything useful, so it's returning a void. And then inside the subroutine G, all it's going to do is to call subroutine F. The no-op instructions are only there to make it very clear that we are inside the body of a subroutine. So that's why I just want to stash a whole bunch of no ops there. And then F is pretty much the same way. F does not really return anything useful. So it really is just returning void. And it doesn't do anything. So that's the equivalence of C and the assembly code. Now, but just looking at the code doesn't really give you any comfort that it is really doing what the subroutine call is supposed to do. So what we'll do is we'll take a look at the program, we'll trace through it, and then see that it works. So we have ASG stabs -o, call return.o, call return.s, LD, call return.o. Oops. Oh, I forgot one thing. Dot global _start. Okay, now we can gdb call return, and we'll stop on the very first instruction, which is on line 27. So we'll stop at the call instruction here. So the first time we trace through this program, I'm not going to show the stack pointer whatsoever. I'm just going to follow the flow of the program, just so that you can see that, oh, calling is really just the same thing as calling, and returning is really the same thing as returning. So we'll single step through this program, run the program, and then we'll single step. I'm at the call G instruction. Where am I supposed to go now? Into the subroutine call line 17, basically. Is that right? Okay. Single step, we are now on line 17. Now we are on line 17, it is supposed to call F. F is defined here. We're supposed to go to line 6. Single step, we are now on line 6. Line 6 doesn't really do anything exciting. Line 7 doesn't do anything exciting. Line 8 might do something exciting. Where do you think we should go after line 8, which is the return from F? We should return to which line?
18.
Line 18, the instruction right after call F. Is that making any sense? Okay. So we'll single step. I think I specified, nope, I guess not. So we'll single step, and we are going back to line 18. Okay, and then we single step the no op, single step the no op. Now we are on the return instruction in G. Where do you think it is supposed to go back to? We are now on line 20. We should go back to line 28, single step, and we are now on line 28. Automatically. Okay, so the big question is, what is the mechanism that allows this particular program to keep track of where am I supposed to go back to when I execute the instruction of return?
The stack?
A stack, exactly. Wow, everything is revolving around the stack. The stack concepts are just stacking up.
You couldn't resist because you jack.
Until we have a segmentation fault.
Or pop off.
All right. Yep.
Your labels don't have to be above start like a function header, do they?
No, they do not. In assembly, the labels can go all over the place. You can do a call to a label that is defined, at the bottom of the program.
And if you took the return out of a label, it'll continue this program from there,
Yes.
making an infinite loop.
Yes. Absolutely. Yep.
So are call and returns just like renamed jumps?
No, they are not. Okay, calling something is not a jump. It has a quote-unquote component of jumping, but before you jump, it has to remember the address of the next instruction on the stack. Okay, so that is the important part. It's in the notes. We haven't really got to that point yet. But when you read the notes on calling and returning, it is there. Okay. But for the time being, it is calling is calling a subroutine F is just call F. Returning from a subroutine is just ret for return. Are there any questions about the concepts of calling and returning? Any questions? Okay. All right. So I think we have all of the components, except that I need to give you the C code to make sure that the C code does work. So I'm going to do the C code first. So I'll just call it flip.c. Count include uni_std.h. Main void. And main just need to call G in this case. And here is G. Void G. Void has no parameter whatsoever. has one single local variable. So the only tricky part is you have to think about how to do the quote-unquote local variable part. Okay, it's already in the program that I gave you. Okay, you just have to figure out which part is actually doing that. And then we have if read 0 for standard in, %ch for the location that I'm saving the character in, and 1 for attempting to read one character at a time. And if this is successful, the first thing we do is we call G again as a recursive function, a subroutine call, and then the second thing we do is to do a write, and then we write to standard out whatever is in CH 1 byte as well. Okay. That's the entire program. So we want to see whether this program works or not. Actually, I can do this all in main. Should have done it all in main so we don't have any other subroutines. Yep.
Wondering, G is calling itself?
Yeah.
How many times though?
Until it does not call itself anymore. Really? I talk about recursion in cisp310 before the C class.
I didn't have a sentence like that. You're a really cool professor. I didn't have you.
Well, there are a few people who took cisp310 from me, and I'm not sure how many remember the concept that is closely related to what we are talking about. Do you remember the return line number thing? Do you remember we allocate the leftmost available column, and then every time you return at the end of a subroutine, we have to look up the rightmost return line number thing, continue execution over there, and then deallocate the column? It's all the same thing.
And it's all up on YouTube.
Yep.
You pull that video.
Yep, exactly. Oh, that's a good idea. I should just replay that video.
There you go.
Yep. Okay, gcc-o flip.c. Okay, so here's the moment of truth, okay? I want to test this with a relatively long file, okay, to make sure that the program does work. And what is better than flip.c itself? So flip is going to flip itself. Self-flipping. And you know what? Even better yet, I can pipe flip to flip, and it should reverse everything back to the original.
Hopefully. Why
Right?
don't you back it up first?
Because flipping is its own reversal, right? If I flip the order and I flip it back, I should get the original back.
Unless you have an error in your code.
Unless I have an error in my code,
Back
or
it
unless
up
I
first.
cheat and just do an alias of cat with flip. Okay, that's exactly what I'm going to do. So flip is going to get its input from flip itself. The output is piped to flip, and then the output of the second flip is going to go to flip.c.out as the output. Okay. How many people know what this command line means? Okay, a few. Okay, I'm going to explain it. The first one is flip, which is the name of the command itself, and then we have a redirect symbol to redirect the input from flip.c. Instead of reading from the keyboard and I have to type everything by hand, it is taking the input of standard in from flip.c. The output is used as the input to the second flip. So the output of the first program becomes standard in of the second flip program. And the second flip program is going to have the output redirected to flip.c.out, which captures the output of the second flip. So I'm running flip twice, okay? The first flip is going to generate the output that becomes the input to the second flip. Now flip is self-reversing. It is its own inverse function. So since I'm applying the inverse function to itself, then we should get the original thing back.
Can you add another output file after the first flip? So you can have two separate output files?
You can, but you can only do it using the T function or the T command. You can basically branch off the input to one program and turn it into two pipes. But the traditional way is the default is only having one output instead of two. All right. So this is the moment of truth because we want to see whether this works or not. Yeah. Because I forgot about the /. Okay. Now, how do we check that those two files are in fact the same? Diff fc, file compare, both will work. So we'll do a diff of flip.c and then flip.c.out, and they are the same. But tag, you might have just aliased, flip with cat, so that's why it works, right? Well, let's take a look, if we capture it in the middle, pipe it to less, does that look like the program in reverse?
Yeah.
It's reversing everything. It's reversing on a byte by byte basis. So it's not only reversing bytes on the same line, it is reversing all those lines as well. So that's why everything is flipped.
Only go to see the bottom.
Yeah, the parentheses, the ordering of the parentheses are flipped, and that's why. Yeah, because we are so used to seeing the open paren first and then the close paren second. So when we see it in reverse, it's like, whoa, what is that? But it's actually just a pair of parentheses, but reversed. Okay, so the program does work. Okay, so what is missing? The missing piece for you guys to figure out is this part here. Okay, if you look at flip, we know how to do this. No problem. We know how to do this. Now we know how to do this. It's just a call. We know how to do this, the right operation. This is the only part that we don't know how to do. Now, when we use a local variable like this in the context of a subroutine, it is by default a auto local variable. The local part we are not too concerned because we don't even need to have it named, but it is local, which means each invocation of the subroutine has its own copy. Okay. So you have to kind of think about what we have talked about today. Okay, what is the mechanism that can create a space for you to store something today? That is what that local variable is about. Yes, it is push. But then you also need a pop at the end because the ordering has to be consistent. So you need to make sure that you deallocate a space that your push has used at the end.
Yep. So when you're pushing that zero, the first program you push to zero, would that be the char CH?
That is allocated. It's almost the same as char CH equals 0.
Yeah.
Because not only are you allocating that space, you're initializing it to 0 as well. Now what is missing here, which is implicit, I should probably write it down because somebody is going to forget and then the program will not work and you get segmentation faults all day long. Is here you have to remember to deallocate the storage that you have previously allocated for CH, which we have talked about also in today's lecture. Yep. Yep. So we have all the pieces necessary to write this program. It is recursive. Now the other piece is to read the notes. Okay, definitely read the part about the stack and also the part about the call and the return instructions. Okay, because those are really, really important. So when you go to the website, we are now on topic 7. The stack is the first one, and the call and return is the second one. Are there any questions about this homework assignment? No questions? Okay. So what I'll do is we have 4 minutes left, which is probably not enough to talk about the practice exam for exam 2, but I'll start that anyway. I'm not going to give you the practice exam right after the break because I promise you that I will give you the exam 1 week from the practice exam date, and we kind of missed that today. So what I'll do is I will give you the sample questions, or at least some of the ideas of the sample questions. We'll go over these questions on the Tuesday after spring break, and then the exam will be on the Tuesday after that. Tuesday. Yep. The second Tuesday.
Tuesday.
So, but we do want to kind of take a quick look here. Sample questions. 1. You have to give me a range of numbers so that if you put those numbers into, that's a malformed instruction. At the EAX, okay, so change that to AL, okay, %AL instead of %EAX. So what range of values can you put into AL to make certain flags turn on and turn off? Okay, so you think about the carry flag, you think about the 0 flag, you think about the overflow flag, and you think about the side flag. Okay, so for each of those flags, kind of think, okay, what kind of value can I specify in %AL that can cause the overflow flag to turn on, cause the overflow flag to turn off. So kind of think in that one. Second question, convert complex addressing mode into using basic instructions such as base addressing mode. So pick any addressing mode that we have talked about already. The find it programs will be perfect examples. Okay, so use find it 1 and find it 2, and then you look at each instruction with the complex memory operand, and you say, what if I can only use indirect and immediate operand and also register operands? Okay, in other words, what if the only memory operand is indirect? How can I implement those same thing, but only using indirect operand as a limitation? So that's what that question is about. Third one is to fix a program with different sorts of problems, like not remembering the dot logo, not remembering the int at the very end, and stuff like that. Okay. Fourth program, or fourth type of question, make up for complex conditional branch statements using more elemental ones. Okay, classic example. The one that you have grown to like JNL. Let's say that instruction does not exist, and you can only use JS, JO, and JMP. How do you use only like several of these instructions to implement JNL? That's an example of the kind of question that you might encounter. Implement a short C++ program in assembly code. So I'm going to give you something that's like maybe 5x2, 5x3, that type of complexity. So you have to actually write the code. Obviously, I cannot run it, but I will be able to spot problems just by going over the code. Second last is spot problems of assembly code that implements a C++ program. So I'll give you a C++ code. I'll give you the assembly code. You have to tell me what is wrong with it.
Which one? Which one?
The assembly code.
Okay. So you're giving us a find the difference.
The intention, and then the assembly code is the implementation. So you have to tell me why the implementation is not doing what the C program is specifying. Okay. Last one is system services, reading or writing, and I'll basically just sprinkle those in the previous category of questions. So it's like there's not going to be one question about the system services.
For this exam, are we looking at computers?
Nope. This is all going to be on paper. Yep. But it is still open book, open notes. Any other questions?
My notes are on Google Drive.
Well, I'm pretty sure that you can print it out. All right. So for those of you who want to, if you want to get started with the program, you can go ahead and get started. I'll give you the name of the project.
That sounds good. Everyone's kind of thinking here. All right.